Section 4.1, quadratic functions and transformations. So remember, with a quadratic, we're talking about the graph, which would be a parabola. And here we are looking at the quadratic form, or the form maybe a quadratic function that most of you are familiar with, ax squared plus bx plus c, where a does not equal 0. And we'll look at that form throughout the course of this chapter, but more closely, we're going to look at something called vertex form. So vertex form is when you have function f of x where you have a times x minus h squared plus k. So this is the vertex form of a quadratic. And make sure when you put this in your notes, you star it, because we're going to be using it a lot today. So we've got f of x equals a times the quantity x minus h squared plus k, where a does not equal 0. And what you have to then recognize is that the vertex, the reason they call it vertex form, is because the h and k make up your vertex point. The axis of symmetry, that line that cuts the parabola into two mirror images, is just x equals the h value, or you can think of it also as the x value of your vertex point. Keep in mind, here we have the parent function, or the parent quadratic function. It's just your standard parabola that has its vertex at the point 0, 0, also known as the origin, and its axis of symmetry is at x equals 0. So before we start anything else, it's just something to keep in mind. It's going to help us apply our transformations and create our graphs that much faster. Here's a bit of useful information. So we can look at an equation, or we can look at the graph itself and determine whether or not we have a maximum or a minimum value from that graph. So when a parabola opens upwards, we have a minimum value. When it opens downwards, we have a maximum value. You can also think about it if you have so let's say like this equation here, you have a negative out in front of your x squared term. That graph is going to be reflected across the x-axis, so it's opening downward, and it's going to have a maximum. So if your a value is less than 0, in this case negative, wrong spot. If your a value is less than 0, meaning it's negative, you're going to have a maximum value. If your a value is greater than 0, meaning it's positive, you're going to have a minimum value. So here we've got negative. Here you've got positive. Then keep in mind, if your a value is a fraction that is less than 1, you're going to see a compression, so your graph is going to get wider, essentially growing slower. If you have an a value greater than 1, you're going to have a stretch. It's going to grow a little bit quicker. All right, so let's take a look at some problems here. Here it says graph each function. How is the graph of each translated, or is translated from f of x equals x squared? All right, so I'm going to go ahead and just graph the parent function. So I know the parent function starts at 0, 0, and then I have points here and here, and here and here. I'm not going to graph all the points, just a few. Then I look at this equation. This minus 5 here is telling me that I'm shifting my graph down 5. So I'm going to take the points here and I'm going to move them down 5. So we have a new point here, 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 and then there and there. So this is our new parabola graph. I don't have all those points, but I've got enough. And so how is it a translation from it? It's shifted down 5. Same thing in the second example. I'm going to start with my parent function. And I know these are the base points. And then I see that I have minus 4 inside the x quantity here. So that means we're going to actually be moving this to the right 4 units. So I'm moving every point to the right 4. So I've got my vertex point is here now. And then I've got a point here, 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 and there. And so now this is what our new graph looks like. Here we're asked to interpret vertex form. So they've given us the equation y equals 3 times the quantity x minus 4 squared minus 2. They want to know what are the vertex, the axis of symmetry, the max or min value, and the domain and range. So here we've got our original equation, and then they've given us our vertex form so we can kind of pick apart what we need. So the vertex is our h and k value, so we can take h and k directly out of this. H is 4. This is minus 2 for k, but it should be plus, so that means they must have put a negative 2 in here. So our vertex is 4, negative 2. The axis of symmetry is x equals h, so x equals 4 in this case. Since our a value in this case is 3, it's greater than 0, so that means the parabola opens upward. So it opens up. And that means that k equals negative 2 is our minimum value. And then domain and range. When you think of a parabola, you have to think of domain and range. And if you don't remember domain and range, here's your quick refresher. Domain references the inputs or the x values for which the graph is defined. Range, same idea, except with the y values. So the domain for a parabola is going to be the same no matter which way it opens. It's all real numbers. The range, however, remember, this has a minimum value at negative 2. So your graph looks something like this, meaning down here we're at 4, negative 2. Right there, that'll work. So that means it's not going to go any lower than negative 2, but then it's going to go up forever. So that means our range in this case is going to be, oops, wrong pen. Let me switch back over. All real numbers greater than or equal to negative 2, because it's going to go from negative 2 all the way up through the other points. It's going to define for all of the other y values. So here, they want us to do the same thing for these problems. We're going to identify the vertex, axis of symmetry, max or min value, and domain and range. So we got vertex, axis of symmetry, then we've got our max or min, and then we've got domain, and then we've got range. All right, so let's do the first one together, and then I'll use the others for practice. So here, if we remember, we've got a times x minus h squared plus k. So that means our vertex in this case is going to be negative 1 and then negative 1. There's our vertex. Our axis of symmetry, x equals negative 1. This number is positive, so that means we have a minimum value. Minimum at negative 1. Then we have the domain and range. Domain, again, same as it is for the other ones, all real numbers. And then your range, since it's a minimum value, it's going to be going up, so it's all real numbers greater than or equal to negative 1. Or you can say y is greater than or equal to negative 1. All right, so now take a second, pause the video, and do the same thing for B and C, and then check your answers when you're done. So go ahead and pause it, and when you're ready to see the answers, unpause it. So for problem B, you should have gotten the vertex to be 4, negative 25. Your axis of symmetry is x equals 4. Because of the negative out in front, we know that this graph opens down, so we have a max at negative 25. The domain is all real numbers again. But the range in this case is all of the y values, or all real numbers, less than or equal to negative 25. Then in problem C, your vertex is 125, 125, or the point 125, 125. Your axis of symmetry is x equals 125. Your minimum value at 125, because this graph opens up. The domain is all real numbers again. And then the range is all real numbers greater than or equal to 125. All right, here we have a problem where they're asking us to graph each function and identify the axis of symmetry. So we can use our transformation rules and properties to help us graph these relatively quickly. Or we could fall back on using the graphing calculator to help us find some of these points, but it's just as easy to apply your transformations. So let's look at the first one. We should be able to identify how the transformations work here. If we know that this is what our parent function for the most part looks like, we can then identify what's happening here. We know we're going up 2, and here we're going right 1. So every point is going to go up 2, right 1. So I start with my middle point here, up 2, right 1, up 2, right 1, up 2, right 1. And so this is our new graph. And if we look carefully here, we should recognize that we have our points in the right place because our vertex should be 1, 2, and our axis of symmetry is just x equals 1. So that means we got the point 1, 2, good, and then our axis of symmetry is just this line here. And so we can start putting together all of the things we've used so far to make sure we're getting these graphs correct. We can do the same thing in problem B here. We know that this is going to have our graph open downwards. It's going to reflect it over the x-axis. This is a move 1 to the right. And this is a move up 4. The other option here would be to just recognize the fact that your vertex point is 1, 4 and start there. So 1, 4, we can put this here. This is our vertex point for this problem. We know it opens down, so we can then model our relationship from there to get the rest of our points. Oops, too far. There we go. And so our graph looks like this. And our axis of symmetry here, x equals 1. Go ahead and pause the video and try problem C on your own. When you're ready, unpause the video to see the answer. And here in question C, we've got our vertex at 2, 5 and our axis of symmetry at x equals 2. And we've got our values accordingly. That 2 out in front of this particular equation is telling us that we have a stretch by a factor of 2. So where our original parent function points were, we would take the y values and we would essentially double them. Here they want us to write a quadratic function to model each graph. They're asking us to write a quadratic function to model each graph. So we're going to have to find some key information to do this. We're going to have to find the vertex. Then we have to determine if there's any stretch or shrink based on that information. All right, so for the first one, we've got our vertex here. That is the point 2, 5. Notice here, if we were to superimpose our x and y axis like this, just make it there, we can see that this particular parabola is growing by its normal standard rate. We've got, if this were back at the origin, we'd have 1, 1, 2, 4. So this one doesn't have a vertical stretch or compression, which is nice, makes it easier. So what we can do is we're going to take our h and k values and we're going to plug them into our vertex form. So a times x minus h squared plus k. There's no stretch or shrink here. So we're going to have y equals, and we don't have an a value, so it's just 1. And we've got x minus 2, because we're going 2 to the right, and then squared, and then up 5. So this is our equation for the first graph. All right, same thing here. We've got, to find our vertex here, our vertex is the point -1, -3. This one looks like it has a stretch, so let's see. If we were to kind of compare, we know that normally it's a 1 by 1 and then it's 2 by 4. Oops, not what I wanted it to do. There we go. So as we look at this, so we've got this point, then it goes 1, 2, and then it goes up by 8. Is it 8, roughly? Yeah, so it's doubling it. So that means our a value in this case is going to be 2. sometimes seeing the a value isn't super easy, so there is another way to do this. So in the first case, we knew there was no a value, but here we know there's probably some stretch. So what we can do, since we know this is h and k, we're going to put this information into vertex form. I'm going to take some space here. Get out of here. Why is it not working? There we go. And we're going to choose another point on our graph. So we've got this point here, which is 1, 5. And we're going to plug that and the h and k in here to try to figure out what a is. So that means let's use the y value that is 5. So we've got 5 equals a times x plus 1. Oops, sorry. We're going to plug in the x value that we have there. So it's 1 plus 1 squared plus, and then, minus 3. So minus 3. So what we've done is we've plugged in h, we plugged in k, but we also then plugged in the x and y point up here. So we've got y, we've got x. So what we're going to do is we're now going to figure out what a is by solving this. So here, 1 plus 1 is 2, 2 squared is 4, 4 minus 3, or actually can't do it that way, sorry. 4a minus 3, there we go, equals 5. We'll add the 3 over, that's 8. 4a equals 8. So a has to equal 2. So what I said before, a is 2. So since a is 2, we can now write the equation for this particular quadratic. It's just going to be y equals 2 x plus 1 squared minus 3. So in the first one, I knew that there was no a value because it was the way it was mapped out. And I also know the growth of the parent function. If you don't recognize it, you're going to have to test a point in order to find your value. I'm going to try this one where I'm testing a point one more time for the third graph. So let's look at that third graph there. I'm going to get rid of all this stuff here so I have some space. All right. So for the third one, let's ignore the rest of these for right now. For the third one, we want to find the equation of this particular point here, or of this function. So the first thing we want our vertex point, which is -4, 2. And then we'll just find another point on the graph here. It's 0, -6. So this is h, this is k. We've got 0, -6 is just an x and y point. So we're going to plug all of this into vertex form because we need to figure out what a is. So we're plugging in values. So the y value is -6 equals a times 0 minus a -4, so 0 plus 4 squared plus 2. Now we just need to simplify this down in order to find the a value in order to know what our equation will be. So 0 plus 4 is 4, 4 squared is 16, so we've got 16a plus 2 equals -6. We're going to subtract 2, it's -8, equals 16a, divided by 16, a equals -1/2. So that's our compression factor. It also flips it over to make makes our function open downward, our parabola, so that works. So now we just need to write our equation using our h and k value and our new a value. So y equals -1/2 x plus 4 squared plus 2. Okay, so it's really important that if you can't picture you can't see the growth of the particular parabola, you need to test both the vertex point and choose a point on the graph. Just for good practice, we're going to go back and take a look at the very first one where I kind of saw and I led you in the right direction, but I will go through it the same way I've gone through the last two, using a point just to make sure we have everything clear that we need to. All right, so getting rid of this and this and this and this. There we go. So here, our vertex we said before was 2, 5. Point on the graph, we can use this one here just because it's out of the way. It's 4, 9. So x and y, h and k. So we're going to get y equals, let's just go ahead and plug this into the vertex form. So 9 equals a times x, plug in the x value of 4. 4 minus 2 squared plus 5. 4 minus 2 is 2, 2 squared is 4, so we've got 4a plus 5 equals 9. Minus 5, you get 4 equals 4a. So a has to equal 1. All right, and so if a is 1, our equation just becomes y equals 1 times x minus 2 squared plus 5. Same thing we had before, except I didn't put the 1 there.